Good afternoon, everybody. I'm Nitin Bahadur, Head of Compute Infrastructure at Uber. My team is responsible for running Uber's compute clusters across the globe. And we schedule Uber's workloads across all these clusters. Today, along with me, I have Min Cai, who's a senior staff engineer at Uber, and who's one of the co-inventors of the technology Peloton, about which we'll be talking about. In the audience, we have Mayank Bansal, who's also one of the co-inventors. And we also have a bunch of Uber developers here who've been working on this technology. In a few weeks from now, my family and I will be taking a vacation in Costa Rica. As I was looking for hotels, I came across this hotel, and it intrigued me, El Faro Beach Hotel. Can anyone think about what relation it could have to me and to all of you guys in general? OK, I'll let you in on the secret. All the rooms in this hotel are made of containers, physical shipping containers. It's one of the eco-green hotels in Costa Rica. Now, my hope is my wife likes to live in a container. A little bit about Uber. We've completed about over 10 billion trips, and we are doing over 15 million trips every day. We are in over 65 countries and over 600 cities. And our headcount keeps growing day by day. We are over 3,000 developers as we last speak. Our business growth has been interesting. From 2010 to 2015, we grew at a moderate pace. But in 2015, we hit the hockey stick curve, where we were doubling our users and our rides every 6 to 9 months. And as this growth was happening, the infrastructure teams were scrambling to make sure that the infrastructure did not fall through. There were New Year Eve nights where engineers used to be at office, not partying and enjoying, but making sure things didn't fail and there were no outages. Fortunately, we are well beyond that, and we are pretty stable now. And to give you an idea of where we have come since then, today we are running thousands of microservices on our infrastructure. We have over 100K containers running per clusters, multiple clusters all over the globe. We have separate clusters for GPUs with thousands of GPUs per cluster. And we run over 1 million batch containers in a day. So let's go to the key point here. Uber Stateless Services today run on Mesos.
Hey, Nitin, are you using Mesos slides? This is KubeCon here.
So I know this is KubeCon, but in 2015, really, there was nothing available that would scale. In 2015, we had to go with a technology that was known to work, and we went with Mesos. And in the middle of 2016, as we were actually deploying all this stuff out, we came to different realizations. We realized that there were a vast majority of use cases needed scale, scale, scale. Our autonomous vehicle division wanted to run jobs that would have 100K tasks, and they wanted to run millions of them every day. Deep learning was taking a long time to complete, and the engineers wanted to run deep learning on hundreds of GPUs every day long. And there was really no scheduling mechanics out there. And as we deployed these clusters, we realized, hey, there's a stateless cluster there. There's a stateful cluster here. There are some bad jobs running. There are daemon jobs running. And all these clusters are really not well utilized. What do we do? Infrastructure is a cost for Uber. And for us, one of the important things was, how do we reduce the cost so we can pass on the savings to our drivers and riders? So we went to look for help in industry architectures. And we saw the Borg paper. And one of the things that the Borg paper said was, if you can co-locate latency-insensitive and latency-sensitive workloads on the same cluster, you can get better utilization. We thought that might be a good idea. If we could reduce the number of clusters, we might be able to buy less hardware, We don't have to provision for our peaks because we can start mingling batch jobs when the real-time services are not that active. And disaster recovery would also be much lesser cost because less hardware. But we had to be careful that our real-time services did not get impacted because of all of this. We didn't want a rider opening his phone and waiting for it to contact Uber servers. So we looked at existing cluster management solutions to see what could solve our problems, get us scale, get us efficiency, but there was no silver bullet. We looked at Google Borg, Yarn, various Mesos frameworks, and Kubernetes as well. But what we realized was Google had not open sourced Borg. If they had, our life would have been so much easier. Yarn folks were not focusing on stateless and stateful jobs. They were happy with batch. And in early 2016, Kubernetes was still in its infancy. We were talking about scale. We were talking about elastic resource sharing. We were talking about large-scale GPU scheduling. And they were trying to figure out system scalability and stability. So we came at a crossroads. We came at a crossroads of, do we keep our business hostage while the cluster management solutions of the industry stabilize? Or do we act and keep our infrastructure up to date with our business? And that's when we took a big bet. And to talk about the big bet, we have Min.
Hi, everyone. So to address the challenges Nitin just mentioned, we introduced Peloton back in 2016. So basically, we would like to build a unified scheduling framework, which could be running on Mesos or Kubernetes. So we can support the collocation of mixed workload, including stateless services, stateful large-scale batch, and as well as daemon sets. Peloton actually integrates with different workloads, including Spark, TensorFlow, Yarn APIs, as well as our internal microservice platform called udeploy, and it can be run on on-premise data centers or in the cloud. So this is a high-level overview of Peloton. On the container execution aspect, we can either use the Mesos master, or we're actually in an active development of hooking up Kubernetes directly to Peloton. And then on top of Peloton, we can support different mixed workload. For example, our homegrown service platform called udeploy, as well as our homegrown stateful framework called Odin, which we can run Cassandra, Elasticsearch, Redis, or MySQL on top of that. On the other big category is all the big data workloads, including Spark, TensorFlow, like Airflow or pipeline execution engines. So now let's take a look at how Peloton fit into the comparison Nitin just showed before. Basically, if we break down all different cluster management systems into multiple layers, so every system has some container execution engine, or which is agent running on each machine. For example, Borg has Borglet, Yarn has Node Manager, and Mesos has Mesos agent, Kubernetes has Kubernetes. And in Peloton, actually, right now we're using Mesos agent as our container execution engine in production, but we can also adapt to using Kubernetes as well. And then on top of that, we have like different layers like resource allocation, preemption, placement, and task and job life cycles. So in this case, Peloton is very similar to Kubernetes. We implement all those functionalities. Then application workflows can be extended on top of that as controller jobs or as like CRDs like in Kubernetes. So this is like a high-level architecture of Peloton. We provide a Peloton API using gRPC. So basically, you can implement any Peloton client, like in Java, Go, Node.js, or Python. And we have our Peloton UI, CLI, and different extensions. Right now, we already have more than 10 extensions within Uber, which talks to the Peloton API. Then on the storage side, we're using Cassandra right now through our storage gateway. But we actually abstract out of that layer, so we can potentially plug in MySQL or other storage solutions. Right now, Peloton is still using Zookeeper as a leader election. Then on the actual core components, we have 4 core components. The first one is we call Host Manager. Right now, Host Manager can basically either talk to Mesos master, or in the very near future, we can have all the Kubernetes talk to Host Manager as well. I'm going to talk about more details down the road. And then on top of that, we have a component called Resource Manager, which is managing hierarchical resource pool trees. And then similar to Kubernetes scheduler, we have different plugins for placement engines. Actually, we follow the same idea as Sparrow. Basically, we can have multiple batch placement engines do a random sampling to get like a big scale or big throughput for batch workloads. And also, we can have a custom or special placement engine for stateless services or stateful services. Then on top of that, we have a job manager, which implements the job and task life cycles. So one key feature for Peloton is we have a pretty interesting resource management model, which is called hierarchical maximum fairness. So the idea is that we would like to have elastic resource sharings between different organizations within Uber. So the idea here is we can have different organizations. They can have some reserved resource, and they have some limit. But how much they can use is very elastic and dynamic. Depends on the demand of that organization, as well as the available resource within the cluster. So they will get some fair shares between what they reserved and then what's the max limit they have. For jobs submitted to a single resource pool, they will have local priorities. So you don't need to introduce any global priorities across the company. This is like an example of hierarchical resource pools Peloton has. So basically, you have a tree structure, and you can break down all the resources into different organizations and teams. And then for each resource pool, you will define what is the minimal reservation you want to give to this organization, which will be guaranteed resource. And then what's the maximum, and also what's the fair share. And how much resource each organization can use is we call it entitlement, which is determined dynamically based on the availability of the cluster. So this actually shows an example of resource elasticity we had in Peloton cluster. So for example, at the beginning, if there's no, we have 2 resource pools. One is for team 1 and one for team 2. Initially, if there's no, the team 2 is not using the resource, then team 1 can use most of the borrow resource from team 2. Once team 2 has more demand, then we're going to preempt the resource from team 1 and give back to team 2. And also, Peloton implemented quite a few resource management features in terms of reporting. For example, we can show you what are the top users who's using resource in the cluster, what are the top resource pools using the cluster, and so on and so forth. Those are features are mostly only in like enterprise softwares. Now, Peloton has been in production for almost more than 1 year now. We are running various Peloton workloads at Uber. For example, we are running large-scale batch workload in Peloton, including Spark, distributed TensorFlows, large-scale map workloads, as well as our self-driving car units, the batch workloads there. So the scale we have right now is like we have like more than 8,000 hosts in different Peloton clusters and more than 2,500 GPUs in Peloton, managed by Peloton today. And we're running millions of jobs monthly and more than 1 million containers every day. So one example is we are running Spark on Peloton. Today, most of companies only have 2 ways to run Spark, actually including now have 3 ways. The first one is running Spark on Yarn or Spark on Mesos directly as individual frameworks, or use the new Spark driver for Kubernetes, which is still in development. Actually, at Uber, we're running Spark on Peloton. We had our Spark drivers, which import lots of features which only Yarn has, like dynamic resizing of the Spark clusters. So you can dynamically add and remove executors. The next big workload we had for Peloton is called distributed deep learning. And there are lots of challenges for distributed TensorFlows, like elastic GPU resource sharing, locality and network-aware placement, and GAN scheduling. Actually, GAN scheduling is very important because when you do a distributed deep learning job, you want to launch all the content at the same time. Otherwise, you will have a data lock situation if you don't have enough GPUs in the cluster. So this is actually a high-level diagram how we are running distributed TensorFlows on Peloton. So it's very similar to Spark model, but instead of like user submitting Spark jobs, we have a deep machine learning platform called Mgmt, which using the Peloton API to submit deep learning jobs to Peloton. And we use Peloton itself to do task discovery, as well as GAN scheduling, and so on. So for stateless service, this actually a diagram shows from Jaeger. We had a talk yesterday and tomorrow, basically we can map all the connectivities between all the microservices within Uber. So as Nitin has said before, we have thousands of microservices. Right now, they are still running on Aurora on top of Mesos, and we are actively moving them to Peloton so we can complete the story of collocating long-running and batch workloads. And also, we are working with our data storage team to onboard, to start POC and onboard storage workloads, stateful services to Peloton. So the target timeline is 2020 H1, because this in 2019, we're going to focus on get all the microservices to be running on Peloton within Uber. Now, let's talk about more about Kubernetes and Peloton, because this is KubeCon here. Why Kubernetes? Of course, Kubernetes, everybody's here because Kubernetes is so popular and so well adopted today in the industry. But Peloton still has some nice features which we haven't seen it's available in Kubernetes upstream yet. But before we did any design or anything, we first went to do some quick benchmarking because we want to have some data-driven analysis. First, what we did is actually we were able to run Kubernetes as well as Peloton as virtual clusters on top of Peloton. So you can imagine basically we containerize both Kubemasters as well as Kubernetes and bring up a Kubernetes cluster on top of a physical Peloton cluster. So this way we can run large-scale testing with limited resource. Like in terms of, for example, we can simulate a 10,000 node cluster with like 500 to 1,000 physical machines. And we basically scale the cluster size from 1K to 10K nodes. And we scale the batch and status jobs from 10K to 100K containers, because that's actually the realistic use case we have today within Uber. And we measured two key data points. One is total time to completion for batch jobs, as well as total time to rolling update for stateless jobs. So first, let's take a look at the data right now. First, what we did is we have a fixed cluster size of 2,000 nodes. And then we launch a batch job of 10K pods, 20K pods, and 50K pods on both Kubernetes using batch API or Peloton API. So we can see here actually Kubernetes batch, the batch controller today in Kubernetes is obviously not well optimized. So it takes more than 5,000 seconds for 20,000 pods. And then for 50,000 pods, it actually didn't even complete after several hours. So we pretty much gave it up. But for Peloton, we can launch all those within close to less than a minute. Now, the second experiment we did is we basically we scaled the number of nodes from 1K to 2K to 5K to 100K. And then we compared Kubernetes with Peloton using 10K pods. And we can see here, similarly, like Peloton has a way better performance. Similarly, we did the same experiment for measuring how much time it takes us to create a deployment with 10K pods, 20K pods, or 50K pods. The similar result, we observed a similar result. Basically, Peloton outperformed Kubernetes in various ways. And the same for rolling upgrades. Now, based on that, we would like to say, hey, can we get the best of both worlds? For example, we can get the whole ecosystem support from Kubernetes and the open source effort here. And then, on the other hand, can we get the performance gains and the scalability of Peloton? Another good incentive is also we have to always running business today. We cannot really shut down the clusters and then bring everything to Kubernetes. We have to have a seamless migration story. So Peloton could solve that problem as well if we have everything under the same cluster. So two possible solutions we have come up. One is we can take the Kubernetes Peloton features and plug them into Kubernetes as a custom scheduler. But that will have some limitations, which like the etcd and API server bottleneck, we still have the same. Then the second solution we come up with, we can hook up all the Kubernetes into Peloton Host Manager, and then provide a Kubernetes API bridge, which will support the core primitives, and then potentially you can have all the CRD resources to build on top of the bridge. Now,
so in summary, Peloton has been running in production for over a year now, and we are solving a bunch of our large-scale business use cases. It was designed day one so that it could run alongside any container orchestration system. And we encourage all of you to go check out our engineering blog, which details a lot about what this technology is, how it's progressed, and what all it can do. We'll open it up for questions right now. Thank you. So I'll repeat the question. The question was that from the performance numbers that we are seeing, do we see a degradation in performance for Kubernetes from the batch framework, or do we see it from other parts of Kubernetes like etcd or API server?
That's actually a very good question. We haven't done really deep dive analysis, but at least our infrastructure or the benchmark can set up us for that. To answer your specific question, for batch, we definitely observe there's a scheduling limitation because it's basically launch all those containers in multiple batches. So it's not like basically if even I have all the resources available in the cluster, the scheduler is not like pushing them to all the machines. It's basically doing like hundreds or 200 every cycle. So it's definitely there's some bottleneck on the scheduling aspect. Maybe it's, I don't know exactly, maybe the scheduling algorithm or because the scheduler is watch etcd every time you get like a chunk of pods, right? So also in Kubernetes, you only get one scheduler. In Peloton, actually, we call it placement engine. So basically, every time you only have one placement engine working. But in Peloton, actually, we have 2 or 3, which will do the same time. So this actually follows if you guys know the Spiral paper. So basically, you don't, the placement engine in Peloton is more intelligent. It basically can do random sampling of the clusters and then do high throughput pushing for the scheduling. Oh, there's no affinity in this case. But by the way, this is also very primitive result. We definitely would like to work with the community to improve both Peloton or Kubernetes side. So.
Yes. We plan to open source it in early 2019.
So I can take this question. So there are two angles. One angle is from Uber perspective, because we build Peloton for Uber. That's one. Uber already have very fancy service discovery mechanism. Basically, we have something very similar to the blog naming service. Same engineer developed that in Uber. So that's more scalable than Istio. Within Uber, we are definitely not going to change that. So basically, the Peloton will still support the Uber internal service discovery system to serve our business needs. Externally, I think we're going to make that also pluggable. Basically, like Istio can work with the same primitive or any other service discovery system. We try to like abstract this out so there's no lock-in or anything.
Thank you, folks. Oh, yeah, sorry. Yeah. Yeah.
So you guys use this for class system, right? So what do you use for time management? Like time scheduling?
So right now we actually don't have, are you talking about a reservation-based scheduling? Or, yeah, we don't have this feature right now. I know Yang has this, and we are looking into that as a future work. No, so basically right now even Yang within Uber, we don't use that feature of Yang anyway.
So is it event-driven? What's the status? Like what fits the status?
Oh, right now we have like different, within Uber we have like very large big data system, right? So there's like Spark, Flink, Hive, all those kind of different batch systems. And basically, we gave them either a Yang queue or Peloton resource pools, and they will submit their jobs. But if they're not using the queue, and because of the elasticity of the scheduler, the other jobs will use resource. Okay. Yeah. So there's no static partitioning of the cluster. Everything is elastic.
Any other questions?